Detectors are divided into two major categories: imaging and spectroscopic. An imaging detector is one that gives a picture of some part of the sky. There are many different kinds of imaging detectors. The first ones, of course, are our own eyes. As I mentioned earlier, for centuries, astronomers simply drew pictures of what they saw. Through much of the 20th century, photography using film or photographic plates was the dominant way astronomers made images of the sky. These had the advantage that they weren't dependent on the astronomer's drawing skills, and they gave much more controlled and measurable results. In the last couple of decades of the 20th century, electronic imaging became dominant in astronomy, just as it has done more recently in popular photography. The device that made this possible, both for astronomers and everyone else, is the charge-coupled device, or CCD. A CCD is much more sensitive to light than chemical photography, and digital images are much easier to work with. In general, imaging detectors allow astronomers to study the brightness, structures, and sizes of astronomical objects. They make it easy to see how one object relates to the other objects around it. You should also be aware that a lot of astronomical imaging is what we call false color imaging. This is one of the things that is particularly effective about digital images. Using a false color image allows astronomers to highlight particular details such as emission of a particular wavelength of light. In the case of light outside of the visible spectrum, this is even more important. This light is translated from some other part of the spectrum into visible for us to be able to see it. So the colors have to be false, or we wouldn't see anything. The other major class of detectors is spectroscopic detectors. A spectroscope breaks light up by wavelength, allowing us to see the spectrum of light produced. On the left, you can see the bright emission lines on this astronomical spectrum. On the right, we can see a spectroscope hanging from the bottom of a telescope. This spectroscope is optimized for use in the infrared part of the spectrum. As we discussed in the last chapter, taking a spectrum allows us to determine a tremendous amount about an object. This includes information such as temperature, composition, and speed of the object. For example, this image shows a spectrum of a planetary nebula, the debris from a dying star. The emission lines in the spectrum match up with those produced by complex carbon molecules called buckyballs. An important property associated with astronomical detectors is the exposure time. This is a measure of how long the detector spends gathering light for any given image or spectrum. Several times each second, our eyes give a readout to our brain based on the light that has hit the eye in the previous fraction of a second. The time over which the light is gathered is called the exposure time. Having a short exposure time gives us the sense that we're seeing continuous images. However, it also limits the faintest things we can see. If we don't get enough photons in our eye in that short time, we don't see anything. A detector can combine light for seconds, minutes, or even hours. Having long exposures like this allows a detector to observe much fainter objects than would be possible with our eye. For example, the two pictures show the same part of the sky on the same evening. The one on the left is a short exposure time. You can only see a few of the brightest stars. With the longer exposure on the right, you can see many more faint stars. Short exposures still have important uses in astronomy. A long exposure will wash out the details of bright objects, while a shorter exposure will allow us to see those details. In addition, a series of short exposures can be used to detect rapid changes in an object or in our own atmosphere. You can have the most wonderful telescope in the world with fantastic instrumentation, but if you put it in a lousy location, it won't do you much good. Location is one of the key things that determines how a telescope works. The most fundamental question about location is whether the telescope is on the Earth's surface or located in space. More than 90% of all research telescopes are on the surface. This is done for the obvious reason that it's far less expensive to build and maintain a telescope on the ground than it is in space. A good rule of thumb is that a telescope in space will cost about 10 times as much as a similar telescope on the ground. So nobody is going to put a telescope into space unless there's a very good reason for doing so. However, observing from the Earth's surface imposes several important limits on telescopes. These include limitations on the wavelengths of light that can be observed, the blurring caused by seeing, and the interference of light pollution. We'll look at each of these in the next few slides. Since the early 20th century, astronomers have realized that one way to avoid some of these problems is to locate observatories on mountaintops. By getting above much of the atmosphere and away from much of the light pollution, mountaintop locations, like this one in Switzerland, offer some improvement over observing from sea level, though not as much as going into space. We're used to the idea that we can see through our atmosphere, but in fact, many kinds of light can't pass through air. This diagram shows what parts of the spectrum can pass through our atmosphere and what parts can't. The dark line represents the opacity of the air. Where it's high, it means light can't pass through. Where it's low, it means that the light can make it to the ground. You can see the rainbow representing visible light. Certainly visible light passes through the atmosphere easily. So do most radio waves. This is why radio astronomy was the first branch of astronomy that was developed outside of visible light, starting in the 1930s. Infrared and ultraviolet light can only partially make it through the atmosphere. Some wavelengths in these bands can penetrate better than others, but they're both difficult to observe from the ground. This can be helped somewhat by observing from mountaintops, especially for some infrared light, which is blocked by water vapor. High mountaintops are often above the vast majority of the Earth's water vapor, so these parts of the infrared spectrum can be observed quite effectively from mountains. There are several telescopes on mountaintop locations that specialize in infrared observing, such as the Infrared Telescope Facility in Hawaii. Another approach to observing infrared without going to space is to use a telescope in an airplane. The SOFIA Observatory is one of only a couple of large telescopes that has been mounted on an airplane to observe from the Earth's upper atmosphere. As you can see, the airplane has to be substantially modified to put a large hole in one side while still allowing it to fly. X-rays and gamma rays are completely blocked by the Earth's atmosphere. Astronomy in these parts of the spectrum, as well as large parts of the infrared and ultraviolet regions, must be done from space. Seeing describes the blurring effect caused by motion in the Earth's atmosphere. This blurring comes about because air bends light, just like glass and water do. This bending is small, but noticeable. Turbulent air will bend light in different directions several times a second. This makes objects in the sky appear to waver, a lot like the view from the bottom of a swimming pool. Even without a telescope, we can notice this when we see stars twinkling in the sky. Through a telescope, turbulence causes the image to look blurry and to bounce around rapidly in the field of view, greatly limiting the angular resolution of the telescope. You can see this happening with this image of a crater on the moon. In recent years, new technologies have been developed to compensate for seeing limits. These adaptive optics techniques actually change the shape of the mirror very rapidly to make up for the fluctuations in the air. To do this, astronomers need a bright star in the sky close to the object they want to study so that they can use its light to guide the mirror adjustment. If there doesn't happen to be one there, they create an artificial star using a laser to light up a small patch of the upper atmosphere. That's what this observatory in Chile is doing. Light pollution is both natural and artificial light that is reflected into telescopes. This has the effect of making dark skies seem less dark so that faint objects can't be seen no matter how big the telescope. While there are some sources of natural light pollution, the main concern is the light produced by humans, much of which is radiated directly up into the sky, where it can be reflected back into telescope optics. This is a major problem for professional astronomers, but it's also an issue for anyone who wants to see the night sky. If you can't see the Milky Way when you look up at night, then you're suffering from light pollution. Light pollution doesn't just affect visible light. Radio astronomers also have to deal with light pollution from the tremendous amount of radio noise generated by people. There are a few things that can be done to limit the effects of light pollution. One of these is to simply locate telescopes far from human habitation. As this global light pollution image shows, this is getting increasingly difficult as human populations have spread out across the globe. For example, a century ago, Mount Wilson, just north of Pasadena, was one of the best observing sites in the world. It now has a severe light pollution problem from the LA basin. Another option is to control urban lighting to reduce the effects of light pollution. Using more downward directed lighting and limiting the wavelengths of light emitted helps limit light pollution. A few cities near observatories have done this. Here are two possible telescope projects. Look them over and describe the strengths and weaknesses of each. Then decide which is more likely to get funded and explain why you made this choice.